Hello everyone. I'd like first of all to thank the editorial-in-chief of IEEE Transactions and Computers for selecting our paper as the featured paper in December 2021. Let me introduce myself. I'm Aray Salahvarzi, a research assistant from Cyber Physical Systems Lab in Iran University of Science and Technology. I'm here today to present our recent work titled Iraqi a robust hybrid on-chip memory kit for the processors with STT-MRAM cache technology. I thought it would be useful to divide our talk into 7 main sections. I will start off by an introduction, then I will move on to some preliminaries about STT-MRAM. After that, I will be looking at the previous studies, and next I will focus on the motivation of this work. Then I will introduce the details of Iraqi, and after that I will explore the simulation setup and results of this work. And finally, I will conclude my presentation in the last section. It will take about 20 minutes to cover these issues. STT-MRAM is a promising memory technology for replacing SRAM in on-chip memories. The motivation of deploying STT-MRAM is its low leakage power and high density. However, high error rate of STT-MRAM cells should be addressed to make it applicable in on-chip caches. Actually, STT-MRAMs are error-prone to 3 types of failure: read disturbance, write failure, and retention failure. Among this, the write failure is the most crucial reliability challenge. Generally, the write operation in a cache memory occurs due to either a missed request or updating the memory block value of a hit request. In both cases, the main factor in imposing write operations to the cache memories is the decisions made by cache replacement policy, as it can directly decrease the number of write operations by decreasing the miss ratio of the cache. In fact, if the replacement policy can reduce the number of missed requests, the number of write operations imposed to the STT-MRAM cache will be decreased. In this work, we explored the effects of different replacement policies on the reliability of STT-MRAM caches through a set of analysis. Also, we propose a set of replacement policies that work together at different levels of cache memory for improving its reliability. Besides, we design and evaluate the architecture of cache memory hierarchy for employing the proposed replacement policies. This figure shows the structure of an STT-MRAM bit cell, which consists of an access transistor and a magnetic tunnel junction, or MTJ. The MTJ is composed of a reference layer and a free layer separated by a tunneling oxide. The free layer can be programmed to change its magnetic field direction, while the reference layer has a fixed magnetic field direction. For a read operation, in the first step, the word line is activated and a low sensing current is applied through the cell to sense the resistance of MTJ. In the second step, if the sensing current is higher than the reference current, the MTJ is in low resistance and the content of the cell is 0. If not, MTJ is in high resistance state and the cell contains a 1. During the write operation, a current greater than the critical switching current is passed through the bit cell. Writing 0 or 1 is determined by the direction of the applied switching currents between the bit line and source line, while the word line is high. During a write operation in STT-MRAM, the content of a cell can change unintentionally due to read disturbance. The occurrence probability of a read disturbance in an STT-MRAM cell is calculated according to this equation. A retention failure occurs when an idle cell flips without applying any intentional excitation source. The retention failure probability is calculated by this equation. Write failure, as another reliability concern, occurs when the magnetic field direction of the free layer in an MTJ is not switched during the time that write pulse is being applied. This equation shows the probability of a write failure for an STT-MRAM cell. To reduce the rate of write failure, some studies increase the amplitude of write pulse. In addition to imposing high latency and energy overhead, these techniques increase the probability of oxide barrier breakdown in STT-MRAM cells. In some studies, the content of memory is read after each write operation, and writing is repeated until the data is correctly written. Extra read operations, in fact, increase the occurrence probability of read disturbance in these techniques. Error correcting codes, or ECCs, have been widely used to tolerate write failures. And these codes increase the read disturbance rate as well as the cache area and energy consumption. But Iraqi improves the write failure probability of STT-MRAM cache by up to 35.4%, and it only imposes less than 1% performance overhead to the system compared to the conventional replacement policies. The write error rate of an STT-MRAM cell is highly dependent on the patterns of values being written. It means that the write failure probability during 0 to 1 and 1 to 0 transitions are different. It is reported that the STT-MRAM write error probability in 0 to 1 transitions is greater by 2 orders of magnitude compared to 1 to 0 transition. On the other hand, the number of 0 to 1 transitions in a cache block are proportional to Hamming weight, which is equal to the number of ones in the incoming block. In our study, we will take the Hamming weight of incoming blocks as a metric for comparing the effectiveness of a replacement policy in reducing the write failure rate in an STT-MRAM cache. We conducted a set of simulations using Gen 5 full system simulator. We fixed the L2 cache replacement policy to LRU and alternatively changed the L1 data cache replacement policy to observe the effects of different replacement policies on the write failure. To compare the effect of L1 cache replacement policy, we have chosen the Hamming weight parameter as a metric. As you can see, this figure shows the Hamming weight ratio of L2 cache incoming write request for different L1 data cache replacement policies. The results in this figure are normalized to the case that L1 replacement policy is LRU. As can be seen in this figure, changing the L1 data cache replacement policy has a direct effect on the Hamming weight ratio of the incoming data blocks that are written into L2 cache. MRU policy considerably reduced the Hamming weight ratio by 16% on average. The chart on the right side shows the IPC, or instruction per cycle, for different configurations, normalized to the case that LRU is chosen as L1 replacement policy. As can be seen, while MRU as L1 replacement policy provides the most suitable configurations for a system in terms of STT-MRAM L2 cache write failure rate, it noticeably degrades the performance of system. Indeed, it is illustrated in this figure that selecting MRU as the L1 data cache replacement policy leads to the worst system performance. According to our observations, none of these policies were able to considerably reduce the Hamming weight ratio and keep the system performance high at the same time. Also, we observed that selecting LRU for both L1 and L2 caches always lead to the best cache performance. As I mentioned before, Iraqi suggests a set of replacement policies for both STT-MRAM cache and upper-level cache to handle the write error rate of STT-MRAM cache and increasing the reliability of on-chip cache hierarchy. At the first step, we need to modify the typical replacement policy of upper-level cache considering two constraints. One, the overall number of write operations that are imposed by upper-level cache to the STT-MRAM cache should be kept as low as possible. And two, Hamming weight of incoming blocks during the write operations that are imposed by upper-level cache to STT-MRAM cache should be potentially as low as possible. In Iraqi, we introduced a new replacement policy for upper-level cache which tries to decrease the overall Hamming weight ratio of data blocks in STT-MRAM cache. So, Iraqi replacement policy uses Hamming weight parameter and traditional parameters used in LRU to conduct both Hamming weight efficiency and performance efficiency. The Iraqi architecture is shown in this figure. In the left side, you can see the abstraction view of the cache memory hierarchy and the target upper level cache considered as level I-1 and the target STT-MRAM cache considered as level I. Notice that our upper level cache is implemented by SRAM and our STT-MRAM cache is implemented by hybrid STT-MRAM SRAM technologies. Actually, the goal of proposing hybrid cache is to benefit from high density and low leakage power of STT-MRAM and high reliability of SRAM at the same time. We modified the typical architecture of the upper level cache. We added a Hamming weight counter as well as a Hamming weight flag bits, and we updated the cache controller. The Hamming weight counter is responsible for counting the Hamming weight of each block that arrives at the upper level cache. This module also provides the cache controller with this information. The Hamming weight flag provides Iraqi cache controller with the required information about the Hamming weight of blocks. To this end, we modified one of the LRU flag bits in tag array of upper level cache to keep the information about Hamming weight of each block. The cache controller implements the Iraqi replacement policy in the upper level cache based on the information provided by the Hamming weight counter and other counting flags in tag array, including Hamming weight flags. Here we have two algorithms, and you can see the inputs and outputs of each one. Iraqi LC controller and replacement policy procedure is called after each access to the upper level cache. If the request that is arrived at the upper level cache is a missed request, at the first step algorithm tries to find the highest value of MHW among the blocks in the target set. In MHW, M is the most significant bit and shows the characteristic of each block from the recently usage perspective. The HW represents the characteristic of each block from the Hamming weight point of view. The zero value in this flag shows that this block may impose high 0 to 1 transitions if it is evicted from upper level cache to the STT-MRAM cache. In fact, for each block in upper level cache, the higher MHW value, the better candidate it is for eviction in Iraqi LC algorithm. After finding the maximum MHW, Iraqi will add it to the victim list. To introduce a victim block, Iraqi randomly selects a victim block from the victim list. After restoring the new block, MHW flag will be updated. Iraqi makes the M flag 0 to show that this block is recently used. For updating the HW, Iraqi compares this value to the HW threshold value. After that, for a hit occurrence, algorithm should update the MHW flags of the target set so that future decisions on evicting blocks will be feasible. The Iraqi SC replacement policy is triggered by the cache controller as soon as a new data block arrives at STT-MRAM cache. When a new data block arrives to be written in STT-MRAM cache as a read miss, HW of new block is compared to the HW threshold. If it is less than the threshold, the LRU replacement policy will be triggered by cache controller to find the target block's location from the STT-MRAM ways. Otherwise, the LRU tries to find a location from SRAM ways. And finally, the write-back request signal and victim block are sent to the lower level memory if the victim block is dirty, or null will be returned if the victim block is not dirty. On a write-back hit, Iraqi should check the HW of the updated block, which is going to be written in STT-MRAM cache to avoid any HW write violations according to the Iraqi SC algorithm rules. For evaluating Iraqi, we've used Gen 5 Cycle Accurate Simulator, and the details of the simulation configuration are outlined in this table. 10 different combinations as multi-programmed workloads are chosen from a Spec CPU 2006 benchmark suite. To find out the HW threshold value, we conducted a set of profiling experiments. This chart depicts the HW distribution of the workloads. The HW threshold can be considered as a knob in Iraqi, and designers should perform a set of profiling evaluations to find out the proper value for the HW threshold. We calculated the HW ratio of the incoming data blocks in STT-MRAM-based part of Iraqi-equipped L2 cache. This chart shows the HW ratio normalized to the baseline. I should mention that in baseline configuration, the cache hierarchy does not benefit from any write failure technique, and both L1 and L2 caches are equipped with LRU. LER is one of the previous studies and is considered as a state-of-art STT-MRAM cache replacement policy. As you can see, Iraqi reduces the Hamming weight ratio of the incoming data blocks by 31.3% on average. Since LER only decreases the 0 to 1 transitions and does not have any control on number of ones, the HW ratio is not affected by LER. The total number of 0 to 1 transitions are shown in this chart. Iraqi reduces the number of 0 to 1 transitions by 30.5% on average, and this value for LER is only 19%. We also counted the number of 1 to 0 transitions in L2 cache. As shown in this chart, on average, Iraqi reduces the total number of 1 to 0 transitions by 11.7% compared to the baseline. While as a side effect of LER, the number of 1 to 0 transitions are increased by 2.6% compared to the baseline. The impact of Iraqi and LER on the write error rate is shown in this chart. Iraqi outperforms LER and reduces the write error rate by 28.7% on average, while the error rate reduction gained by LER is 17.5%. These charts show the miss rates of L1 and L2 caches for 3 configurations. As can be seen, LER and baseline have the same miss rates because the L1 cache replacement policies in both of them are LRU. Since the replacement policy of Iraqi in L1 cache is modified, it imposes about 2.2% miss rate overhead. For the L2 cache, as can be seen in this chart, Iraqi imposes about 1.8% miss rate overhead, and this value for LER is about 2.4%. We've chosen IPC as a metric for showing system performance. The IPC overhead is shown in this chart. As can be seen, Iraqi imposes less than 0.9% IPC overhead on average, while LER imposes 1.2% IPC overhead. We have used Synopsys Design Compiler to extract the information about area and energy consumption. The dynamic energy consumption is shown in this chart. Our results show that Iraqi not only does not impose any energy overhead to the system, but also decreases the overall dynamic energy consumption by 3.55% on average. And LER increases the total dynamic energy consumption by 1.9% on average compared to the baseline. As illustrated in this chart, Iraqi increases the total static energy by 1.3% on average, while LER increases the total static energy consumption of L2 cache by only 0.2% on average. The only extra element in L1 cache is the HW counter, which imposes a negligible amount of 0.25% area overhead to the L1 cache. Allocating two ways of SRAM in L2 cache increases this cache's area by 2.1%, and the Hamming weight counter unit only imposes 0.08% area overhead to this cache. Let me just run over the key points again. STT-MRAM technology benefits from a number of advantages like non-volatility, low leakage power, and high density. But STT-MRAM suffers from reliability challenges where the write failure is the most critical one. 0 to 1 transitions in write patterns are the main contributor to the write failure. In Iraqi, we modified STT-MRAM cache and its CPU side neighboring cache in a way that Hamming weight ratio of the incoming block is reduced so that the write error rate in STT-MRAM is decreased as well. Our experiments showed that Iraqi reduces write failure rate by 28.7% on average. I sincerely appreciate that I have had this opportunity to present to you. Thank you so much for your interest and attention.